I am Sharon McAuliffe, and I have the honor of serving currently as the chair of the Notre Dame Senior Alumni Board. And the Senior Board is very happy that you have joined us today for our inaugural academic seminar. The Notre Dame Senior Board is charged with engaging seniors to connect to the university, to connect to each other, and to connect to our communities. So senior alumni are anyone who are 60 and older, and if there's any of you that were part of the senior alumni when you turned 55, you're still with us, and we didn't kick you out, and we're happy to have you. So what do? The Senior Alumni Board connects to the local clubs with individuals who are known as SACs, Senior Alumni Coordinators. And the Senior Alumni Coordinator's job is to create events that seniors want to participate in. There's a list there: museum tours, wine tasting, community service activities. And I'm sure you can't read this, I don't expect you to, but this is a listing of the activities that are going on around the clubs in the country for the months just of June, July, and August. So if you haven't read your issue of the Golden Domer, which I'll come back to at my conclusion, you can go and find events that are happening in your community. So we're hoping that you connect to your local club if you haven't done that already. What else does the NDSA do? We also have a couple national initiatives. One of those is the God Country Notre Dame Scholarship. The God Country Notre Dame Scholarship helps military men and women and their families. And in addition, we try to honor someone every year who has improved the lives of others through volunteer service. And that award is called the Putz Award, and it is given in honor of Father Louis Putz, who came up with this idea that senior alumni are a very valuable group and should continue to be engaged by the university. We have a golf tournament. It'll be our 5th golf tournament this fall in September. This raises funds for the God Country Notre Dame Scholarship. It'll be September 26th, just before the Virginia game. We would love to have any and all of you and your friends attend. There are a number of other board members that are here, so if anybody has questions about playing, there's information there. There's also some information on our webpage. And if you can't make it to campus, we would be happy to have you or your business or your club sponsor the tournament. And Jack Leitch, class of 74, one of our board members, is here. Jack would be happy to talk to you about that. So if you haven't been engaged with a senior alumni yet, please consider it, and please let us know if you have any interest. We can be found on Facebook. We can be found on the Notre Dame website at My Notre Dame. And then there is the Golden Domer newsletter, which I hope all of you are receiving. This lovely woman that made you wave a few minutes ago is Janine Sterling, class of 76. She's a board member of NDSA, and she is our wonderful editor of the Golden Domer. So we thank you for joining us for our inaugural lecture today. I'm now going to turn it over to another one of my board members, Stan Bernat, and he is going to introduce our speaker today.
Thank you, Sharon. Good morning, everybody, and I'm so glad that you decided to come to this program instead of running the marathon this morning. So I know it was a tough choice. I'm pleased to introduce today our Notre Dame's senior alumni academic speaker, Professor Joshua Koen. Professor Koen is an assistant professor at the University of Notre Dame Psychology Department. He's completing his first year of work here at Our Lady's University. Professor Koen received his undergraduate education from the University of Texas, Arlington. He received his MBA and master's, I'm an MBA side of things, sorry about that. Master's of Science and PhD from the University of California, Davis. His postdoctoral work experiences include work with the Center of Vital Longevity at the University of Texas, Dallas. Understanding from interviews at the University of Notre Dame that northern Indiana weather closely resembles that of both Texas and California, Professor Koen relocated his family to South Bend. No surprises, I'm sure. Incidentally, Professor Koen's wife, Denise, works for the Notre Dame Police Department here on campus, and please remember to thank all of our safety forces for all their services. At Notre Dame, Professor Koen continues to research in cognitive neuroscience and teaches undergrad and graduate programs in the cognitive neuroscience of memory and aging. Professor Koen's research aims to understand the neural processes that support encoding of memories that can be subsequently recollected. I'm hoping Professor Koen can tell me where I left my car keys last night. Professor Koen has an impressive history of peer review published articles in publications such as the Journal of Cognitive Neuroscience, Memory, and Neuropsychology Review. In 2019, Professor Koen was included with other Notre Dame professors in the funding award of the Notre Dame Science of Wellness Initiative's Catalyst Seed Grant Program, sponsored by the university's Provost Thomas Bursch. Please join me in welcoming today Professor Joshua Koen.
Well, thank you for that great introduction, and thank you all for having me here this morning. Maybe by the end of this talk, you might have wished you had ran the marathon, but we'll see. So, just want to get started. That is not where I want to be. So, just to kind of provide an outline of my talk today. So, I'm just going to really start off talking about aging and why it's important for society. And a little bit about Alzheimer's disease, because that's really kind of the main thing as we grow older that's becoming a bigger concern. And then I'll kind of get to one of the main topics of understanding how memory changes as we age and how the brain changes and supports memory as we age. And lastly, I think the most important part is I will talk about potential lifestyles and interventions, or lifestyle factors and interventions that you can do to help promote support cognition throughout your life, in essence, to improve vital longevity. So when I talk about vital longevity, I'm referring to this notion that as we grow old, our society is growing older. We're expected to live longer through advances in a lot of medical technology. This expectation of, or this longer life expectancy isn't necessarily associated with living what we would consider an active lifestyle. So we might live longer, but sometimes there's a large proportion of those years we might live in poor cognitive health or poor health in general. Not surprising, our society is aging, and it is projected to age very rapidly by 2015. So this is basically a population pyramid, and the most important thing from this is to see, if I can get a mouse up here, there we go. So the population that is over age 70 is expected to exceed about 10% of the world's population by 2050, which is a very substantial portion of the population. And this is important because it really does have a lot of societal and economic impacts, such as medical expenses and other factors that can influence family life for children as well. Also, one of the aspects about our population aging is this increased prevalence of dementia, and particularly Alzheimer's. Now, Alzheimer's is the type of dementia, but it's not the only type of dementia. But it is the most common. And Alzheimer's is largely a dementia associated with aging. So as we increase from, let's say, 70 to 75 years of age, our risk of developing Alzheimer's disease increases. And this risk increases every 5 years or so quite dramatically. So part of the research I'm involved in and the research my field is involved in is identifying the factors that predict Alzheimer's and might help prevent cognitive decline associated with Alzheimer's disease. Because it's largely a disease of advancing age, if we were able just to delay its onset by 5 years, we can in essence have the case of Alzheimer's, which is quite dramatic. I will say that this endeavor is something that is really challenging, and it's obviously going to take a long time for our field to be able to do this, but this is kind of the ultimate goal. So Alzheimer's disease was initially, the first case report of this occurred in the early 1900s with Dr. Alois Alzheimer seeing this patient, Auguste. This patient presented with very severe dementia, and they couldn't remember where they were. He described this really as a disease of forgetfulness. In subsequent works, brain examination of this patient, but also subsequent work with Alzheimer's patients, what we found is that there are particular types of brain abnormalities that are associated with Alzheimer's. So in Alzheimer's, this is kind of a picture of a brain that is suspected of having Alzheimer's, and you can see that there's just a lot of kind of space between these folds in the brain, which is not normal. That's actually very excessive, and that's one thing that's associated with Alzheimer's. Plus, there is severe atrophy in regions of the brain that are critical for memory, as we'll talk about, and this is a region collectively known as the medial temporal lobes. It's kind of right here in this area. It involves the hippocampus and surrounding parahippocampal gyrus. And what you can see in this example is it's really not much there. It's atrophied, it's shrunk, there's been a lot of cell loss. In addition to this kind of volumetric change and structural change with the brain, there's also neuropathological features of Alzheimer's, such as the development of plaques, which are these extracellular protein buildups that can lead to cellular damage, as well as tau tangles, which are it's a type of protein buildup within a neuron that can actually really critically damage the neuron, and is actually what's associated with a lot of the Alzheimer's neuropathology. So what's really unfortunate, we talk about Alzheimer's being a disease of advancing age. By the time we start to see the symptoms of Alzheimer's, it is something that the pathology for Alzheimer's has already kind of done its damage. So those features I talked about with the brain, those typically occur 5 years, 10 years, or even more than 10 years before you actually start to see the clinical symptoms of Alzheimer's. So for example, the buildup of the amyloid beta, which is this purple and red line, might start 10 or 15 years before you actually would get to this little green area, which is where you would actually start to see cognitive impairment, see the actual behavior of an individual, a loved one that you know, starting to be affected. So our work is really aimed at trying to identify these early features as early in our lifespan as possible to try to push this curve to the right. So basically, we just kind of push it towards, closer towards where life expectancy is, so we don't have to experience so we kind of stave off the onset of Alzheimer's disease. So Alzheimer's is a really big concern because it does affect the medial temporal lobe, which I mentioned is really important for memory. And memory is, I think, one of the features most of us would agree is critical to our lives. It's not just remembering what we have to do, where we need to go. It involves some other critical functions like remembering to take medicine, remembering to pay bills, but also in the form of memory I'm more interested in, which is episodic memory. It really gives us a sense of who we are. It's our experiences from our past that inform our personality, our character, and our current actions and help us to make decisions as we move forward and gives us a sense of purpose in this world. So memory is one of the biggest factors that changes as we grow older. So overall, cognition does decline as we age. These are particularly present in a lot of tests that involve, let's say, memory and attention, and other ones that involve doing things quickly that we call processing speed tests. But not all forms of our memory or our cognitive capacity changes as we age. In fact, some actually can get better compared to younger adults, such as general world knowledge or vocabulary. Now, this graph is a little misleading, I think. So it kind of looks like, if we were to kind of follow it, if we look at where the 30s are, we start to see that we've declined from 30s to 20s, and basically it starts right after you left Notre Dame. And that's not really true, because if it was, then I would be in that falling portion already. So this is This is a cross-sectional study, and so what this means is that there was a sample of 20-year-olds tested, 30-year-olds, 40-year-olds. This is not the same individual over time. So this doesn't necessarily give you a representation of what happens throughout someone's lifespan. But this does give you a general idea that some things do decline. And I'll show a graph later, which is actual longitudinal data, which will kind of, I think, make this not seem so bad. So I really want to distinguish between two types of memory that I think are really kind of big in my area. And these are types of declarative memories. And declarative memories are types of memories that I can say happen. I can declare it happened. This is not like a procedural memory such as riding a bike or driving a car, for example. So we have the two different types we might distinguish between are semantic memory and episodic or autobiographical memory. So a type of example, an example of semantic memory might be remembering that the first president of the United States was George Washington. Or the geography of the United States, where the states are or what the names of the states are. Or for young adults today, I like to put this in there, how to write a check. It's something that they don't necessarily know how to do. But this is kind of one of those examples of what a check is. So the reason these are semantic memories, if you think about this, if I was to ask you who the first president was, you probably could tell me that it was George Washington. But now if I was to ask you this next question of, well, where were you when you learned who the first president of the United States was? What were you doing at that time? That's another contextual detail that you don't have. And that type of contextual detail is the type of memory I'm interested in, which is what we refer to as episodic or autobiographical memory. So these are examples of some very simple everyday things like where you parked your car. So we park our car every day. We might park it in a big parking lot. So where we park it today versus yesterday. And that could be a really important thing. Or, as Stan was mentioning, where you put your keys, because we put those down every day. It could also be other examples of which might have actual relevance, like what you had for breakfast yesterday versus today. And this might be relevant because, let's say you get food poisoning later in the night. You might want to try to remember exactly what you had that day so you can link it to something. I say that from experience. I had that earlier this year. But these can also become more personal. So for example, the first time you took your daughter, which this is my oldest, Olivia, she's now 8, so she's really young in this picture, and my wife, the first time we took her on a camping trip and we went to this state park in Texas, which is Dinosaur Valley State Park, where in this riverbed you can go kind of look at all these dinosaur tracks that have been left. So these are the types of memories that I'm interested in. These episodic memories are really the ones that change as we age. So this is an example of the longitudinal data I was talking about. In these red dots, you see this trajectory of episodic memory. So what you can see from this is that from my age, about 30, 35, till about 60 to 65, it stays relatively level. And this is after you've controlled for a bunch of potential confounding factors. And then after about 65, it starts to decrease, and it actually starts to accelerate the amount of decrease that happens. Whereas with semantic memory, memory for kind of these general facts, it stays relatively constant. If anything, maybe gets a little bit better in middle life and early, late adulthood. And then it might start to decline really, really late in life. So episodic memory is one that is largely affected as we grow older. So we know that this happens, and this episodic memory is really these specific details about a prior event. So we also know that as we age, there's a lot of changes that happen in our brain. The structure of our brain changes, its ability to function properly changes as well. I don't want to say properly, but its functional properties change as we age. So how do we link these two things together? And this is really the focus of the cognitive neuroscience of aging field, is linking brain to behavior throughout the lifespan. So one way we can do this is we can examine patients with damage to a particular region of the brain. So for example, this would be a patient with damage to their right frontal and temporal cortex. This could be for things like a stroke or a car accident or other types of diseases that can just cause these kind of rapid acute changes in the brain, acute damage in the brain that persists. So in regards to memory, I just want to give some example. Now, this isn't necessarily addressing anything related to aging, but this is just addressing the basics of memory in the brain, is the case of patient HM. He's one of the most influential patients in the memory literature. HM was an individual who had intractable epilepsy. It was drug resistant, and he just had really severe seizures a lot. So at the time, his doctors, they had localized or thought the seizures were localized to the mediotemporal lobe, this hippocampus and surrounding area, which is really critical for memory. And so, well, we didn't know it was critical for memory at the time. But they localized it to this region of like, well, if we remove this tissue, we can stop the seizures. And largely, they did. So they went into a surgery and they removed the mediotemporal lobe. There was an unintended consequence, though. This patient was left unable to form new memories. He had severe interrogated amnesia. So I didn't put a picture of it, but Dr. Joshua Koen, who worked with patient HM a lot and made a lot of important discoveries, wrote just a really recent book. It's called Permanent Present Tense. It's about patient HM. And it's actually a really good read if you're interested in reading more about that. But he led to this idea that, well, the mediotemporal lobe is really important for memory. And now I really just want to show another video of this. And this is another patient. His name is Clive Waring. He had, I believe it was viral encephalitis, which affected the mediotemporal lobes as well. And his amnesia is quite dense. And this is just an example of what it is, this type of amnesia might look like in a very severe case. This is actually probably one of the most severe cases. So this is about 3 minutes, and we will just let it go.
One man is consigned to live entirely within the present, with terrible consequences. Clive Waring has the worst case of amnesia ever known. 20 years ago, he lost his memory, and now his wife, Deborah, is the only person he recognizes.
Clive really only has less than 30 seconds memory, and sometimes it's as little as perhaps 7 seconds. It's as little as a sentence.
I'm going to see your sister, Adele. Her daughter's got married recently in New Zealand. And so they're having a party.
Funny how the ladies acquire different title when they get married.
Do you know who I'm going to see tomorrow?
Buckingham Palace.
No, really guess.
I don't know.
You don't know? Adele.
Oh, I see.
Do you know why I'm going?
No.
She's having a party at her house tomorrow.
It's her birthday, isn't it?
No.
No.
Do you know why?
No.
It's to do with her daughter.
I see.
Do you know why her daughter's having a party?
No.
Guess.
No, I don't.
She's just got married.
Oh, I see.
She just got married in, do you know what country she just got married in?
No, I don't.
In New Zealand.
Oh, I see.
Yeah.
The sentence he is in, he will probably have forgotten the sentence before. You ask him a question, and he'll give you an answer, but while he's giving you the answer, he's already forgotten the question. That's how short it is.
I'm going to see your kids tomorrow.
You want to see my kids?
Yeah, your children.
What are they up to now?
Do you know what they're up to now?
No.
Guess what you think they're up to.
No idea, I couldn't guess. I don't know what their O-levels were. They hadn't got an O-level last time I was conscious. So I didn't know what possible thing they could do, did I?
No.
No, I couldn't possibly guess.
Where do you think they are?
No idea. I don't know where I am.
Yep.
All he has
Well.
is void behind him.
It's been like death. I've never seen a human being before, never had a dream or a thought. The brain has been totally inactive, day and night the same. No thoughts at all. As far as I'm concerned, the doctors have been totally incompetent. I've never seen a doctor the whole time. Oh, look, it's come.
So that last little bit where he gets up and runs back to his wife, all she did was walk out and walk back in. And it was like he hadn't seen her in weeks. And that really is his case. So I showed that video. Yes, I understand it's a little sad. Clive Waring. And this is the reason I think these patient cases are important is because they really, kind of tell us about what we expect the normal role of the hippocampus and other brain regions to be to memory. In this case, in Clive Waring's case, to kind of memory in the real world, not in necessarily these lab-based tasks. And the idea is that by identifying what these brain regions are that are important, how they contribute, we might understand that if they change with age, how we might expect memory to change, and maybe how Alzheimer's might develop and how memory might be affected by Alzheimer's in that way. So brain damage is not the only way to link memory in the brain. New advances in technology have been very important in this endeavor. Because the problem with doing patient research is you don't ever really get like what we would want in science, which is a nice, clean, controlled lesion to the brain. It just doesn't happen that way, unless you do animal studies, and still it's not perfect. And also when you have brain damage, there's a lot of things that happen. You're typically on medications, or you've had a lot of trauma. And we might want to look at, well, how does the brain function in healthy individuals? Magnetic resonance imaging, which if you've been in an MRI before for any other purpose, can be used for this. It's a technology that produces really high resolution images of the brain, so we can look at brain structure in the living human brain. We can look at kind of the brain volume, the volume of the ventricles, the integrity of these white matter tracts that connect different brain regions. But also, with some new techniques, we can examine brain function, or at least a correlate of brain function, where we can measure blood flow to brain regions while you're doing a particular task in the scanner, and kind of link that blood flow, which we think it signals something about increases or decrease, or something about neural activity, to cognitive performance. So, for example, we can measure the structure. You might not be able to see the structure of the hippocampus and those surrounding regions which are highlighted. That's the medial temporal lobe. Or we can measure brain function, which is an example of what a resulting image might look like after we've done months and months and months of data analysis on the image. So we know that the structure of the brain changes as we age. Now, although overall there's a loss of total brain volume and an increase in the size of the ventricles in the brain, we know that not all brain regions change or shrink or reduce in volume to the same degree. The largest changes associated with aging are in regions in the frontal lobe, particularly the prefrontal cortex, as well as the temporal lobe, and most importantly, the medial temporal lobe. So that's where we see the largest shrinkage in the brain, or the volume loss in the brain. And what's really important is both of these regions play a pivotal role in memory, in both memory encoding and retrieval. So we do know that the hippocampus gets smaller as we get older. So this is an example of an MRI with different regions of the medial temporal lobe traced out. And the important one I want to point to is here, is the blue one, which is the hippocampus. It sits very right in the center, surrounded by a lot of other brain tissue. And on the right is data from a longitudinal study, where they had participants come in and get scanned at 2 different time points. These individuals started off at around age 55 and went all the way up to the last session was around age 85. And from that data, from those 2 different time points, we can look at kind of the average change in hippocampus across time. And that's what, it's kind of hard to see in this graph, but that is what this solid gray line is plotting. It's just kind of the average shrinkage of the hippocampus across these 2 time points. And what we can see, is not surprising, is as we go into our from 60 to 80, the volume of the hippocampus decreases. The hippocampus is getting smaller. And what's really interesting is that the shrinkage of the hippocampus can predict longitudinal changes in episodic memory. Now, these episodic memory changes are from a typical lab-based word learning paradigm, where I might have you sit in a chair across from at a table across from me, and I read you some words, and then I have you recall the words, and then I read you the words again, and have you recall the words again. That's a standard neuropsychological memory test. And they had this data, because it's a big ongoing longitudinal study, from where they had 15 years of changes in episodic memory performance. So they can look at kind of the average change across this long period. And even over the shorter 4-year period where they had the neuroimaging, what they found is that if you had a lot of change, which is lower on this y-axis, so down here would be more hippocampal volume loss. You also performed more, you had a larger amount of reduction or lower memory performance. So this is just some evidence, not in addition to the HM and Clive Waring, that the hippocampus, particularly as we grow older, can contributes to episodic memory. But we know also that structure is not the only thing. So it's not necessarily that bigger is better in the brain. We also know that the functional integrity of the brain plays a very critical role in memory. So this is kind of a common example, and in particular, the brain activity that happens when we first experience something might be really important for determining whether or not we can remember that. So an example of this might be when we meet someone new. So we meet someone and we go, he's like, hi, my name is Bob, and we want to remember this face of this person with this name. We call this aspect of memory encoding, and this is largely what I study. And some of the big questions that we're trying to ask in this kind of paradigm is, does activity in some brain regions predict memory performance, and how does this differ between young and older adults? Are older adults recruiting the same regions as younger adults to do the same thing, or does that change? Do we adopt maybe different strategies or have different other neural mechanisms that help support memory encoding? So we can do this using that technique of functional MRI, where it's a measure of blood flow in the brain. And the way we will do this is typically just have participants view pictures or words on the screen, and we have them make a judgment about these words in the scanner. And the judgment's really so people pay attention to it. If you have been in a scanner, you know it's oddly easy to fall asleep in an MRI machine. It doesn't sound like it would be. It's this little small thing that you're in, and it's making a lot of loud noise, and then you're in it for 2 minutes and you want to like sleep the entire time. So this might be an example of the task where I show this flower and I go, okay, this is something I'm likely to find outdoors. This hot air balloon, I'm likely to find outdoors. The bed, I'm likely to find indoors. And this chair, I might likely find indoors. This is a horse outdoors. Oops, that went off really bad. So basically what we're doing is while participants are making these judgments in the scanner, we're recording their brain activity. And then afterwards, we'll take people out of the scanner and we'll send them from another computer, and we will test their memory. So we'll show them those pictures they saw on the scanner. But this time we'll also add some pictures they haven't seen before. And just have people determine, did you see this picture, yes or no? And so if I were to show the flower, I can ask, during the study phase where we scanned, when the neural activity associated with this flower, was this associated with something a trial that was later remembered? So did someone accurately go, yes, I saw this flower at the test phase? And we can look at this example here, which this would be like a new item. And so this would be one we want an individual to say, no, I didn't see that. And then we might have this chair where someone may have forgotten it, and that happens. Or it just might not be accessible. We just might not be able to retrieve it at that point in time. So this is something we would classify as being forgotten. And we can contrast brain activity for those trials that are remembered and trials that are forgotten and look at what we call a subsequent memory effect. And this is basically just brain activity during encoding or learning or first experience with something that predicts us going on to remember it. So I want to just really focus on the prefrontal or the frontal cortex for this little portion of it. We do know that brain activity in the left prefrontal cortex predicts accurate during the learning phase, predicts subsequent memory in both young and older adults. So these bars here, basically what they're showing is the difference in activity. So if they're positive, that just means it's predicting memory performance, or you're remembering. You can view it that way. But we also know that, so basically what this is saying is that when the left frontal cortex is active during a new event, we're more likely to remember it than to forget it. The right frontal cortex, however, and this is something that is, I will say, is under a lot of debate. In older adults, it's not just the left frontal cortex. It also seems to be that we engage the right frontal cortex. So the right frontal cortex shows the same pattern where you get this increased activation in the right frontal cortex that predicts memory. And the idea for some is that this might actually be a compensatory mechanism. It might be either, let's say, a strategy that we use to learn new things, or it just might be a neural mechanism where we're recruiting another brain network to help support declines in another brain network to preserve our memory function. That is a very open question, and it's like I said, it's still under a lot of debate, but that is one of the ideas. So that last portion was really meant to link memory to the medial temporal lobe and to the prefrontal cortex, and show that memory declines as we age. These brain regions decline in structure and function, or change in structure and function as we age, and these are related to the memory declines we experience in old age. So this last portion of the talk, I want to really just kind of discuss some potential lifestyle and factors and interventions that are being looked at to ideally ameliorate cognitive decline as we grow older. So one thing that hasn't been apparent in some of these figures so far is that the trajectory of our cognition throughout the lifespan is highly variable. So it might fall anywhere, let's say, in this gray area. So you might have some individuals who start off high and they stay really high performance until the end of their lives. But you also might have some individuals who start low and stay at the bottom, but you might have individuals who start low and they engage in the right type of lifestyle factors, for example, and they go, in the case of like A, where they get really, really good, and then they start to decline off towards the end of their life. So so the idea is that there are so many factors that contribute to this. They could be lifestyle factors that help promote and improve our cognition and memory as we grow older. They also might be interventions to where we are maybe following the normal trajectory of cognitive decline, but they help just kind of flatten it out for a period of time before we start to decline again. And then we might just have, the average expected decline. So many of these factors, these factors are, there's quite a few, and some of the ones that are being looked at the most are social, environmental, and genetic factors. And I'm really going to focus more on the social and environmental factors than the genetic factors. But I will say that the genetic factors, although there are some, so for example, there's a particular variant of a gene called the apolipoprotein E4 gene, which is just APOE gene. And this gene can have some detrimental consequences for aging. It's associated with increased risk for Alzheimer's, but there are some of these interventions that can really kind of dampen that negative effect of the gene. So there's this idea that all these things interact together. So all of this research really, I want to say it's in its early stages. We have a lot of epidemiological studies, which are just looking at an association across the lifespan. What we don't have a lot of is necessarily kind of randomized control trials where we can establish a causal relationship yet. So there are two strong predictors of cognitive longevity in terms of benefiting cognitive longevity. One is consistently engaging in mentally and socially stimulating activities. And the other, which is why I said you might have wanted to run the marathon this morning, is aerobic exercise. Although maybe running a marathon is not what's needed, it's more like maybe brisk walking or just basic cardiovascular fitness. There is a strong belief that these activities might slow cognitive aging and also might enhance our cognitive functioning in late life. So I just want to provide a couple of examples about these. So I'm going to talk about a study which was actually led by the founding director of the Center for Vital Longevity, where I did my postdoctoral fellowship. And the whole notion of this was that if you engage in new skills and learn new skills, this can benefit memory as we grow older. So in this study, which was a really intense study, and I'm amazed that they pulled this off, they recruited older adults and had them in two different conditions. So one, they had what they called a productive engagement condition. This is for, I want to say it was like 12 to 14 hours a week, these individuals attended a class. And this might have been a quilting class that involved other people, or a photography class where you learn how to take photos and edit them in Photoshop, which if you've ever worked with Photoshop, it's really hard to learn. The individuals did this over time, and they tested their memory at the baseline before they started, and then they tested their memory after completion of the engagement period. But they also had a control condition, which was receptive engagement. And this had a bunch of different aspects to it, but it really didn't involve some of these social integration or mentally stimulate, or it didn't involve the social interaction and the learning of the new skills. So this might have been things like listening to classical music at home, keeping a daily diary, where you're kind of engaging your cognition to some degree, but you're not just being sedentary. And so what they found is at the beginning, at the pretest, there was no difference in memory between the two groups, which is really important for these types of studies because of the difference at baseline. It becomes really challenging to know if the intervention's helpful or if it's just something you had different groups of people. This receptive engagement condition, which is the blue bar, did benefit memory over time. So it's not like this wasn't beneficial. It's just this productive engagement was much more beneficial. So you saw a larger improvement in episodic memory across the lifetime, or across this training period. So, yeah. Another idea is this whole notion of mental stimulation. So this could be learning new skills, or this could just be engaging in mental activity and doing lots of things that aren't just necessarily, like I said, being sedentary. In this other study from that's now actually over a decade old, so apparently I have times on my slide, and I did not know that. This group, I forget which longitudinal study this is, but they have a large sample of participants they're following, in this case 775, and they follow them longitudinally, and basically they just ask participants to rate their level of mental stimulation. They had a questionnaire that evaluated this. And so and they were examining risk of Alzheimer's disease. So these individuals had were not diagnosed or had no symptoms or signs of Alzheimer's at the initial testing. So what they found, they broke their groups up really into this high and low mental stimulation groups. So after 1 year, they were evaluating Alzheimer's yearly, and then after 1 year, you saw for the low mental stimulation group, they started to diverge. So you started to get an increased risk of Alzheimer's in the low mental stimulation group compared to the high mental stimulation group. And as the study progressed, this got much larger. So at the end of the study, which was 5 years, individuals who were reported really having low levels of mental stimulation had about 2.5 times more likely chance of developing Alzheimer's disease. So this really kind of led to this hypothesis about the use it or lose it. And it's not wholly true, to be honest, but it is also one of these things where engagement is really important. That's kind of the notion of this, is that you staying mentally engaged. Another example of this will be physical activity. So we know moderate levels of physical activity can be beneficial in old age. It can lead to better brain health as well as heart health, which is really important. It can lead to improved memory and cognition, as well as improved mood and well-being. Mood and well-being plays an important role in cognition as we grow older. Actually, as we age, depression becomes more likely. And this can actually lead to cognitive decline as well. So for example, moderate aerobic exercise can affect the brain in important ways. And by moderate aerobic exercise, I'm talking about these studies have done things like a brisk walk intervention, where individuals will walk daily for 15 or 20 minutes at a brisk pace, and they'll do this kind of intervention for a year. They'll do that 3 to 4 times a week. So in this one study, they examined quite a few older individuals, and they scanned them 3 different times with MRI, and they looked at the hippocampus volume, which we know is important for memory. And what they found is that the volume of the hippocampus increased. The blue bar is showing the individuals in the aerobic fitness condition, and their hippocampal volume increased throughout the course of this study, so it got larger. Whereas those in the control condition, which this is just like a stretching condition, so they're just doing standing stretching, they're not really getting their cardiovascular fitness heart rate up, for example, their hippocampus showed the standard types of decreased volume. Although this next slide is a different study, it gets at a very similar point, is that in this one, they just measured individual step counts, which is a correlate of aerobic fitness. And they found that particularly in older individuals, the more individuals walked or had the more steps they had taken over a period of time, the better their memory performance was. In particular, their visual memory, but this also led to other things like their verbal memory, as well as memory for face name associations, which is something that is really important for social interactions. So, in conclusion, there's still a lot to learn about exercising and the relationship between exercising, cognition, and the brain. But this one quote in a very recent book chapter by some authors who are leaders in this field, I really just think strikes this point home. And they state, we can be certain that maintaining a healthy heart is critical for maintaining a healthy brain. And part of that, in some ways, you might be able to see with how we measure brain activity with MRI. We're looking at blood flow. We're looking at how the brain is one of the most metabolically demanding organs. It is the most metabolically demanding organ in our body, and it receives a lot of our blood supplies as well to function normally. So having a healthy heart and having a healthy cardiovascular system is going to lead to a healthier brain. I will kind of conclude this little bit on a couple of potential other interventions. So the National Academies of Sciences, Engineering, and Medicine have kind of really been looking at this issue. This has been looked at in large scientific bodies. There is some encouraging evidence for quite a few of the topics I've talked about, as well as some others, but it's at present probably a little inconclusive as well. So cognitive training. If you notice, I've probably left this one out when I was talking about the intervention. So you've heard about these things, brain training games where you can do them on your phone, and are those beneficial? And the answer is they can help. They can definitely help on what they're designed to do. So if you are wanting to improve your ability to play a video game, like play video games, for example, or play these brain training games. What's still, I think, an open question is how training in this one small area, like maybe, let's say, improving our ability to, our short-term memory, our working memory, to maintain something in mind and manipulate it. We can train that and have that be really well, but does that transfer to other aspects of our cognition? So this is a notion of what we call FARD transfer. And that's something that's still not firmly established. Blood pressure management. So again, cardiovascular health is associated with cognitive decline. So there's a new kind of area of research that's getting a lot of attention right now, looking at the relationship between hypertension and cognitive aging. And differences between controlled versus uncontrolled hypertension and how we can and potentially improve cognitive health in old age if we manage our blood pressure. And also, as I discussed, increased physical activity. I do want to say I'm not a physician, so I'm not going to sit here and recommend any of these. These are obviously any of these types of things you would want to talk with your physician about. And I will say, at present, there really is insufficient high-strength experimental evidence to really justify kind of a big public health campaign for this. This doesn't mean that these things aren't important. They most surely are. But by high-strength experimental evidence, a lot of what I mean is like these randomized control trials, like you might think for a clinical drug trial. Kind of doing these things where we take people, we randomly assign them to a condition, and we see what happens longitudinally. Those studies take a lot of time, and they're just now really underway. And just to kind of recap, we're living longer as a population and as a society, and our mental capacities decline, and that can create a lot of potential burdens going forward, and things that, as a society, we probably need to start addressing now before we're not ready for them. We are also, at present, really learning a lot more about how age-related changes in the brain impact our mental abilities, and that really by identifying that some parts of the brain, particularly those associated with higher-level cognition like memory, decline faster than others, and that there's these different patterns of brain activation during memory tasks that we're trying to figure out what those mean and what they mean for cognitive aging. And really that if we keep our mind active in old age and that we exercise and increase our aerobic fitness as we grow older, that might help to stave off cognitive decline. So that is all I have. I'm looking forward to any questions you have. And thank you all again for the invitation and for listening. So I don't. So the question is medications such as particularly Zoloft, I think was the example you gave. Does long-term use of a medication impact the brain? The answer is most likely yes. I don't know about that particular drug, and I can say that that is a particular confound that we struggle to deal with. Not just in brain aging studies, but in other studies like comparing depressed individuals with major depression to individuals with or other psychiatric disorders like major depression, schizophrenia to healthy controls, is we do know that medication can have effect, for example, on volume measures. And so it's kind of hard to know sometimes if what we're looking at is a brain, let's say a brain volume difference that's due to something that we're really interested in, or if it's due to a side effect or an effect of a medication. Yes?
If someone has a stroke and loses some of their cognitive abilities, what can be done to bring any of that back? And assuming it's not a total situation.
Yeah.
Someone who's there maybe 2/3 of the time now and is out of it the rest of the time.
Yeah. So that's a really tough question to answer. Oh, sorry. Yeah, I knew I was going to forget that at one point. So the question is, what can be done if you have a stroke, or if someone has a stroke, to really kind of return cognitive function to normal? And part of that really depends on where the stroke is, the amount of damage that's done. Sometimes people can make what appears to be a full recovery. Other times, there's no recovery from it. And part of it is really the brain has a hard time repairing itself, particularly if you have like a stroke or something, because you get scar tissue and the neurons have a hard time kind of making connections through that scar tissue. So, I mean, I do know with some of, like, if you have a stroke and it's like in your left hemisphere, which is for language, a lot of times, like, you really just, it's kind of like you have to learn all over again. You just engage. It's kind of back to this engagement question. That's really, I think, the most important thing, but I really can't answer much more than that.
You had one slide in which was a combination of the size of the hippocampus, I believe, and the ability to function. But it's a scattergram almost, with a very thin trend line in the middle of it. Do you have any thoughts on that? Do different people function just that much better, even though they have less hippocampus?
Well, so yes. So there is definitely a relationship, and you're right. So the question is, on one of the plots, it was a scatter plot, and so it's just a correlation. And so that line is just plotting a line of best fit, which is, if I didn't have those points, basically the idea is that if your hippocampus had shrunk this much, this is where I would predict you to be, where it would intersect that line. So yes, there's a lot of variability around these lines. And so the hippocampus is definitely associated with things like cognition and particularly memory, a level of memory performance. But we do know a lot of the times, and particularly in volumetric studies, we're kind of taking one brain region and looking at how that relates to this other variable, like this cognitive variable. But there's this really big trend now in cognitive neuroscience, which I think is for the best, where we're starting to look at the brain as a system of networks. So the hippocampus doesn't act in isolation. Like if you remove the brain around the hippocampus isn't going to do anything. It has no inputs to it. So it depends on inputs and communication with other brain regions. So that could be part of why that's the case, so it's not as strong as it is. So it could be that an individual who's low on hippocampal volume but high on prefrontal cortex volume is able to actually maintain high levels of memory performance because it's a combination of the two. Okay, yes.
I've heard sort of the flip also, that physical activity, great. How about the other side of meditation, where you're sitting quietly?
It's a good question. I honestly don't know the answer to that. And so the question is, what about the other side, meditation? I do know, and now this is from my PhD work and just watching other students do this. They actually, I forget the lab's name, but there was a group at UC Davis who would go to some of these meditation retreats up in Tahoe and would study kind of cognition in individuals who went through a meditation training period. It does seem to have some benefits, but I can't speak to whether if it differentially moderates aging across the lifespan.
What about diet? Eat more asparagus, drink less hooch.
So diet is definitely one of, so I think the big question is diet. Diet is definitely one of these things that's becoming more recognizable. So if you've ever been in like a big physical fitness program, a lot of the times they will tell you, part of working out and getting stronger is like 20% of that activity and like 80% nutrition. And some of these actually some of these effects that we see of aerobic exercise on cognitive aging can really be eliminated with a poor diet. So diet is important. The question is kind of what aspects of the diet are important. So there's some aspects like some people, I think there's two that they really look at. One's like a Mediterranean diet, and the other is what they call, its acronym is DASH. I cannot remember what that stands for. And so there's some, we're not sure really, I think, what aspects of the diet are important, if it's a particular approach to maybe having healthy fats versus other types of fats, or fish versus red meat. I think that's still a big open question. And there's some questions up there.
What about genetics?
James. Okay, so so with genetics, genetics play, so what about genetics? Genetics play an important role. So there's, the influence of genes on cognitive aging is really complicated because most of our behaviors aren't coded by just one gene. So there are some risk genes associated with Alzheimer's, such as the APOE gene. A particular variant of it makes you more likely to develop Alzheimer's, and another variant of that same gene actually can be protective against Alzheimer's. They can also affect the trajectory of cognitive aging. There are some genes for Alzheimer's that lead to, so most Alzheimer's that we refer to, we can refer to it as late onset Alzheimer's. So this is the more age-related one. There is early onset Alzheimer's, which really will start to onset around like the middle 50s. And this would be something that is more genetic in nature by these other genes, presenilin and the amyloid precursor protein. And what's really interesting about all these genes is that the neuropathology associated with Alzheimer's, particularly amyloid, they all are related to the buildup of amyloid protein and the cleaning of amyloid protein. So the reason this seems to be important is the graph I showed at the very beginning where amyloid is the first thing that kind of comes about. There at least is a hypothesis that amyloid like sets the stage for all the negative aspects of the other Alzheimer's neuropathology. So the buildup of amyloid allows tau to come in and do damage to the brain, which becomes irreversible. That's kind of it. So
I have a question about, so much is talked about legalizing marijuana.
Mm-hmm.
And I want to know your opinion on the effects of marijuana on the brain. There are long-term effects,
So I do know studies have been, so the question is, what about marijuana and long-term effects on the brain? I actually don't have an answer to that because I've not read that literature personally. I can ask a friend who actually does this research. He's actually, I've got to review something from his later today, where he does research on THC and psychedelics as well, which is kind of interesting. There definitely are effects. And I just cannot tell you which direction they go, and I'm sorry about that. Yeah. Oh.
One more.
Oh.
All right, one more, and we're going to have the big part. First part, we talk about the deterioration in volume of the hippocampus.
Mm-hmm.
That suggests maybe in a general classification, we're talking about brain atrophy.
Yes.
Okay, in that case, when you do this research, individual cases, test for hearing and hearing loss.
So the question is, when we do, so does hippocampus relate to atrophy, or is it related to actual atrophy in the brain? And the answer to that is yes. And then the other question was about hearing loss. Do we measure hearing loss? Not a lot of studies have done that, but it is extremely important. And it's not just hearing loss. We're talking about kind of basic sensory function. And this was something recognized in the mid to late 90s, and it's this kind of notion of theory. It's called a common cause account. So the idea is that we have sensory decline, hearing. We lose high frequency hearing most prominently as we grow older, and we have other types of hearing loss. But we also lose things like visual acuity. So and those might also be driven by kind of this common cause where it's related to brain atrophy as well. So there is a really strong relationship between all of those. I will say, like, kind of one interesting little tidbit in my own research. When we are doing these aging studies, we really want to focus on healthy aging. And by healthy aging, I mean aging not associated with cognitive impairment. So we have individuals come in and do a neuropsychological test battery, where we just want to make sure that they perform within normal range for their age, both high and low. And we typically, if you look at the raw scores and compare to younger adults, older adults show the typical pattern of lower memory performance and everything like that. But it wasn't the largest effect I've seen in my hands. In my hands, the largest effect I've seen of aging on anything I've measured is actually visual acuity. And what's really interesting about the visual acuity thing is this was visual acuity measured when everyone was wearing glasses or contacts. So it suggests it might not even be just like a lens or a cornea thing. It might be something more on retina and transfers to the brain. Yes. Okay. Sorry. Yeah, I'll get it after the talk, okay?